let us start this lecture 2. Before getting into this lecture 2, what we will do, we will try to recall what we learned in the last lecture. In this course, what we will be looking at aerothermodynamics of the propulsion. That means, we will be looking at how to convert this energy into the thrust power. So, that is the basic idea in this course, and subsequently in the last lecture we discussed about how the propulsion evolved in terms of history. Now, I ask a question, why really we want to look at history? It is important because we need to learn the way they have developed the processes, such that it will be useful for today to apply it, such that our future will be better. And we will look at those things some portion, and let us look at Leonardo da Vinci, really who devised this chimney jack. And if you look at, these are the pictures which is I have shown here, and this is your a turbine which will be rotating, and this turbine is connected to this shaft through a gear trains, and also a lever pulley which is joined with this roasting pit. And how does it work? If you look at it, basically burns this wood which is being burnt to provide the heat to this roasting spit. What is that? It is basically a flesh which is being to be cooked, and this spit will be rotated. Now, and this burning of this, what you call this flesh or a meat, the burning of this wood will be producing the gas, and this gas will be passing through this, what you call the turbine, which will rotate it. If you looked at, this is the first concept which was being sketched by a Leonardo da Vinci, who is not involved in the science activities. However, he was known as a greatest artist, and he illustrated this application of reaction principle, right. So, now we will be moving into the first flight of the aircraft, and which had made a epoch in the history of aircraft propulsion. So, if you look at, it was basically done by these Wright brothers in December 1903. He flew the first flight, and if you look at his flight, is pictures I have shown here, that this is the flight which is here, and it is having a propeller which is not visible in this figure, and Orville piloting this flight, whereas Wilbur is standing here at the wing tip to look at how it is flying. Do you know what is the duration of time it flew? It was only for 112 seconds, and it could cover 120 feet kind of things, and after that it was nosedive. But however, it made an history. But if you look at these two brothers who worked relentlessly with lot of failures. If you remember that first slide I showed you, that with frustration that Orville told to his brother that man cannot fly for next 50 years, but they proved that yes, it is possible. So, therefore, engineering per se, it is being done with a lot of failures. But if you look at today's mindset, that first failure make us to be depressed, so that we will leave that and go somewhere else. Engineering cannot be done that way. I must tell you, and those people who have developed the engines or any other kind of success they got all those things with persistent effort and with a lot of failures. So, therefore, failure is the pillar of the success as being told, and they used a what you call a inline engines, and which we will be discussing about it, and it is basically a 4-cylinder water cooled vertical engines, and the figure is shown, and it is being done by designed by a Charlie Taylor. If you look at it, is not a single man job to have an aircraft or any engineering product. It is the group work which is very essential, and whenever you are working in a group, and you will have to adjust with the people, and which is lacking in the present modern India, that we became more secluded and single minded. That will not fetch us engineering. So, therefore, this is the quite good lesson we should learn from this development, and it was really created a history. Now, this after this development, the most of the aircraft is being propelled by the propeller and with the help of power plant known as IC engine. And of course, the air breathing engine concept was given by a genius, I call it René Lorin, and who gave a concept taking from the piston engine. I will show you a figure here, and in this case this engine is basically connected with a nozzle, which is, you can call it as a conversion diversion nozzle, and this is the cross sectional view, and this is the number of nozzles which are connected to a inline engine. If you look at this, is basically inline engine, and he gave this concept of piston engine, converting piston engine to air breathing. That means, is basically a concept of jet engine you can call, and of course, the piston engine is an air breathing engine, because it takes the air and use what you call for burning the fuel. So, it is an air breathing engine. However, the jet engine concept was given by René Lorin in 1908, and he gave another beautiful concept in 1913 AD, and which is the ramjet engine that we use today for the missile applications. And if you look at this, is having a what you call a diffuser, right, or air intake, which of course work in a supersonic flight, and it is having a combustion chamber and a nozzle. So, if you look at it, is not having any rotary components or any complicated components. It is a mere duct which you give the thrust. So, if you look at, these are the concept which was given by Lorin, and he is known to be a great innovators. So, what is important for engineering is innovation, and person should be creative in nature, but unfortunately today we are not that creative, because of fact that we are working quite hard and always busy in something or other, but the man innate nature is creative. I always say that man is a creative creature by nature. Unfortunately, modern education system and the society is not allowing us to go back to our own nature and develop and work for others. So, coming back to that, I will tell you that this after that subsequently 1939, there is a person German Hans von Ohen who developed the gas turbine engine, but most of you will be telling me that it is the Whittle, Sir Whittle, who developed the gas turbine engine, but it is actually the von Ohen who, when he was a student in a PhD student in the Georgia Augusta University at the age of 21 and enrolled as a PhD program in physics. He was never an engineer, and he got annoyed by the noise and vibration created by the propeller piston engine in his lab. And then he thought about, why not have an engine which will be smooth enough and it will not cause any noise or vibration. At the same time, it will give you a large amount of power as compared to its own weight. And that idea was lingering in his mind for quite some time till he finished his PhD. He did not run away from the PhD program. He finished his PhD, and then he requested is Professor Paul to write a recommendation to another person whose name is Henkel. Henkel is a basically proprietor of a aircraft engines, and then he introduced. Henkel was very encouraging, but at the same time he is a businessman, he was a businessman and he was reluctant to take up this thing. He convinced as a young person and worked hard with a lot of constraint and came up with a engine which cross section I have shown here. It is having a air intake and then there is a radial compressor, there is a combustion chamber and it is having a turbine, right. And he flew that in 1939 as the first aircraft to be flown by the gas turbine jet engine. So, if you look at, and this is the first engine ever engine was being flown by the turbojet power, in which hydrogen as a fuel is being used. Today people are contemplating to use the hydrogen as a aviation fuel for aircraft because of stringent pollution or the problems being faced by across the globe. And he was the first person, but he was never considered as an inventor of gas turbine engine because of fact that the German lost the war in the Second World War. So, therefore, he was, but fortunately, and I am also very delighted that in 1991 he was considered or was accepted by the worldwide as an inventor of the gas turbine, co-inventor of the gas turbine. Look at the fate. We always think, oh, I did not get this, I did not get that, but he waited. Of course, he was alive at that time and he could manage to be known as a co-inventor of the gas turbine engine, which was due, but he was not given because they lost the war. And of course, at the parallelly for winning the war, before that there was the First World War. During the Second World War, the Britishers were trying hard to have an engine, and the Sir Whittle developed a engine which I have shown here. In this engine, if you look at, this is your what you call the centrifugal compressor, and this goes into a combustion chamber which I have shown. This is known as a reverse combustion chamber, a reverse combustor, and which was quite compact in that, and then it will be expanded in a turbine which is a radial turbine or centrifugal turbine. Of course, the nozzle it will be expanded and you will get the thrust. So, if you look at this reverse combustor is coming up well again after lull, and however, lot of work has to be done on that to have a compact micro combustors, which I will not be discussing about it. However, if some of you are interested, you can look at it. So, this is the development of the gas turbine engine what we could see, and of course, in India we are having a ambitious program of these aircraft engines and also the spacecraft engine, and we could manage to develop a light combat aircraft in 2001, and which is basically smallest lightweight multi-role combat aircraft in the world, whose dimensions are given, and length is 13.2 meter, height is 4.4 and span of course, the 8.2 meter. So, if you look at, it can cover a Mach number 1.6 to 1.8, it is a technology fly by wire, and of course, the gravity limit is 9 plus 9 g to minus 3.5 g, and keep in mind that we are yet to get a engine of our own, and this light combat aircraft being propelled or being powered by the General Electric F404 and GE IN20 engines. And you must be aware that we are having a research establishment known as Gas Turbine Research Establishment GTRE, which is instrumental in developing a engine. Unfortunately, we are not very successful in spite of a lot of money being spent. I wish some of you will contribute for the development, and it is important to have such kind of engine not only for having a combat aircraft but it is also required for civilian aircrafts and other applications. So, we need to augment our technical know-hows and knowledge to develop certain things which will be useful. So, beside this we are having a plan what you call ambitious programs of launching vehicles. One of them which I am showing here is GSLV, which all of you will be aware. This is a geosynchronous satellite launch vehicle which was developed in 18 April 2001. There are several versions which have come up till now, because already 11 years are over by this time, and which will be, if you look at it, is having a 4 Strapan motors, and each is having a booster rocket engines, and there will be first stage and second stage, which we will be discussing little later on, but just to give you a brief idea I am just talking about it. Now, having come to this brief history of the propulsion, let us look at how we can classify a propulsive device. As I mentioned earlier, that propulsive device can be broadly classified into two. One is air breathing engines and other is non-air breathing engines. Air breathing engines means is basically the which will breathe the air. This is the air breathing engine, that means it will be taking air as an oxidizer, and you can use as a fuel like your piston engine, gas turbine engine and other place. But however, this can be restricted into the what you call in the atmosphere only, but when you want to go beyond atmosphere, naturally you do not get the air, because atmosphere will not be there and air is not there, means oxidizer or oxygen will not be available. So, therefore, we will have to look at another class of engine for aerospace application, that is the non-air breathing engines, means it will be carrying not only the fuel, but also the oxidizer. So, these air breathing engines can be broadly divided into two categories. One is your constant volume engines, and what is the example of constant volume engine? Like your piston engines, right? It can be spark ignition engine, it can be what you call compression ignition engine or the diesel engine. And there are several other varieties like Stirling engines, and then your Brayton engines can be used, Brayton cycle can be used in the piston as I told, but it is not being used. However, there is another class of engine which is known as constant pressure engine. What is the meaning of constant pressure engine? During this combustion process, pressure will be remaining constant, right? How that possible? That is a matter of discussion. We will do that whenever we will get into that. Now, let us look at how this constant volume engine can be divided into the IC engine, that is the internal combustion engine. That is another class of engine which you call it as the external combustion engine. However, for propulsion we do not use it. Internal combustion means the combustion will be taking place inside the engine itself. And there is another very compact engine which I will be discussing little bit, is known as Wankel engine, which is not being used very much. However, it has a potential to be used for several aerospace applications, particularly air breathing engine class. Whereas, the constant pressure engines is divided into the ramjet engine, which we will be discussing to some extent very briefly little later on, and turbojet engines, turbofan engines and turboprop and turbo shaft engines. So, all these things we will be discussing as you go along. Let us look at how we can classify these non-air breathing engines, and it is can be divided into three. One is photon engines, photons, that means photons light particles, and which is basically will be collected in the outer space and can be used, but this is not in a very what you call developed stage, rather I would say that it is very infancy stage. And there is a solar cell which is similar to that of photons, but however, it will be having a panel which will be collecting the photon from the sun, and then converting into the various forms of energy, whether it is a what you call a solar cell, or it can be any other thermal kind of things. What we will be interested in basically the rockets engines, and these rocket engines will be divided again into electrical and thermal and nuclear. That means, electrical energy will be used in the electrical rocket engines, which I will not be discussing, but however, which will be using the what you call is a thermal engine, which will be main focus of our discussion of this course. That is, we will be discussing about solid propellant engines and liquid propellant engines and hybrid propellant, that means combination of solid and liquid, which we will be discussing, and towards the end of this course we will be discussing about this more. However, for the completeness sake, we will be now looking at some of these concepts little bit further. And let us look at a schematic of IC engines. You know that I have taken a cross sectional view. It is having various components. One is of course the piston, and other is your connecting rod, and there is a crankshaft. In this case, the piston and the crankshaft, it will be helped to convert the translation motion into the rotary motion. And in this case, there is a inlet valve through which, whenever it will be opened, through which the air will be entering into it, and we can have a fuel which is mixed together, or it can be injected directly. In this case, it is basically mixed beforehand and coming, and when it will be compressed again, as the piston will move from the bottom dead center to the top dead center. At the end of compression, there will be ignition with the help of spark plug, and then the combustion will be taking place, which will be pushing the piston, and thus the power will be generated, and that is known as power stroke, during which the piston will move from top to the bottom dead center. And then when the piston will move from the bottom dead center to the top dead center, the combustible or the what you call the exhaust gases will be going out through this valve, and that completes the cycle. Of course, this is known as the 4-stroke engines, but however, there is a 2-stroke engines which is coming up again. It can be utilized in future, and unfortunately, I will not be covering in this course the piston engines as such, although a large number of aircraft even today, if you look at the number wise, are being powered by the piston engines. And in our flight lab, we are having 7 aircrafts which are being propelled by the piston engines. Therefore, I would ask you people to look at it and learn yourself, and maybe some of you can write a term paper on piston, aero piston engines, which is different than the automobile. Based on the cylinder and piston arrangement, we can classify the engines into 4, but of course, you can have more, but here I have shown the 4 type. One is inline engine. If you can look at, there are several piston cylinders are connected to the same crankshaft, but with different phase angles, so that it can move tandemly or move in a continuous manner without much fluctuation in the power level on the load on the crankshaft. And another kind is the V type, and which is piston and the crankshaft being connected through this to the shaft in such a way that it will cancel each other along this what you call horizontal force, so that the balance will be better. And there is another opposed piston arrangement, which is shown here, that both these pistons like are opposing to each other. For example, this is at the top dead center, this is at the bottom dead center kind of things, both the vertical. It can be vertical and it can also be horizontal. The basic idea is that the shaft should run smoothly and without this thing, but this is not really being very much used in aircraft engine. However, inline and V types are being used, and so also the radial. In the radial, the piston and cylinder are being arranged along the radius, so that it will be the power will be transferred to the shaft in a very smooth manner without much fluctuation on the load and other things. So, we will be discussing a little more in the next slide, that is in inline and radial, which are being used very much for the aircraft engines. So, under this category I will show you two engines. One is inline engine, as I told that it is being used by the Wright brothers, and which is having a cylinder. These are the cylinders which is lined up in one row, and if you look at generally piston on the top, but here in this case pistons are in the bottom, and this is the crankshaft which is having a shaft which is shown here, and to which the propeller will be mounted, and this is being done because our propeller can be mounted easily and better ground clearance you can have, because the propeller size is higher. So, you can test it well and put it. So, therefore, this kind of engine which is being used, and it is having a narrow frontal area and lower drag can be, therefore, it is being used in the engines. And of course, there are several V engines which is together being used, and there is another engine which you can see in our flight lab, which is being kept as a model, I guess. It is a rotary engine. That means, the cylinders, these are the cylinders which are being mounted along with the thing, and as a result it will be well balanced, right. The balancing is a big problem in the IC engine, you might be aware, those people who have studied the mechanical engineering will be knowing that. So, it is a cylinder arranged around the crankcase like a radial engine, and it is a bolted, the propeller is bolted to the engine, like this is the place where it will be bolted, and it is a generally a 2-stroke design, as I told that engines can be 4-stroke and 2-stroke. It is having higher specific power and high power to weight ratio. Of course, there are several disadvantages of that, severe gyroscopic effect and difficult to fly, because it is little bit heavy in nature, right. So, it is not being used nowadays, however, it was being used earlier days. So, I will be discussing about Wankel engine. I am very much fascinated by this engine, because it is quite compact. It works on a basically 4-stroke of a typical Otto cycle in this engine. You can look at in this animation that air is coming over, this is known as air intake. It will be compressed, and then once it compressed, then the ignition, the combustion take place over here, and then it will be expanded and it will be going to the exhaust. So, this is a quite a compact engine, and of course, lot of people, a lot of research groups across the globe are working, and in India NAL, that is National Aeronautical Laboratory, is working on this engine for a quite some time, and I was told it is in operational mode at this moment. This Wankel engine can be used not only for the aircraft, but also for the what you call the automobile and auxiliary power units and other things. So, I will just show you a cutaway view of the Wankel engine. It looks to be quite simple as compared to that, but it is a quite compact at the same time. And if you look at these epileptic gears, and this is the chamber where the combustion, and then air will be coming inside, and then it will be reacted somewhere here igniters, and it will be going out. So, this engines is a quite a promising one according to me, but unfortunately, it has not been used in real situation. I hope and wish that it will be worked, maybe some of you will be looking at it if you are having interest in engine like this. So, let us look at a gas turbine engine. Basically, it is a gas generator which I have shown here. This is having a compressor, is having a combustion chamber, and this is having a turbine, and these constitute the gas generators. And whenever the gas generator is connected with a nozzle and an air intake, which is not shown in this figure, is considered as an aero gas turbine engine or turbojet engine, right. So, as I told you, this is the air breathing engine, and the combustion takes place in this place, which is at a constant pressure, right. That is why it is known as constant pressure engine. And as I told you, what will be happening here, when air will enter into the air intake, there will be increase in pressure, because the kinetic energy is converted into pressure energy, and then it will be further compressed in the compressor, and there is a combustion chamber where the heat being added, and it will be expanded in a turbine, and it is expanded further in the nozzle to produce the thrust. So, if you look at, I have shown the schematic diagram here, there I have showed you a cross sectional view, which is air will be entering into compressor, and this is the combustion chamber, and the turbine, keep in mind that turbine will be producing power, which is just meant to run the compression. It will not be giving you any thrust, and of course, the thrust will be obtained by expanding the gas in the exhaust nozzle. So, that is basically what you call the turbojet engine, and there is another class of engine which we will be discussing, but let us look at a cross sectional view, which is similar to that of the turbojet engine. However, it is having little difference, that is, apart from the core engine or the gas generator, it is having a big fan and also a nozzle, right. And this we can also nozzle when it is expanded, the gas going through the fan, it can produce also some thrust. And beside this, there is a nozzle, exhaust nozzle in the core engine, which will be producing the thrust. So, total thrust by the engine can be obtained by both the fan nozzle and the exhaust nozzle. And there might be a situation where both the fan stream and the core stream mixed together and then can be expanded. There is a various varieties of these turbofan engines which is there, and keep in mind that it is being used very much for high subsonic aircrafts. However, it gives a lot of drag as well as compared to the turbojet engines. So, what are the advantages and the what you call disadvantages we will be discussing little later, but keep in mind that it is heavier than the turbojet engine, it is having more drag. However, it is being used in the your passenger aircraft or the civilian aircraft like Boeing kind of class. So, let us look at now a schematic I have just shown you, and I have already discussed about this thing. You just look at animation what really happens. In this case, it is having a 2 spool engines. What is the meaning of this 2 spool engine? One is low pressure spool, that means there is a shaft which is will be the low pressure, like a low pressure turbine, which will be here, will be connected to the your fan, right, and whereas the high pressure turbine, which will be somewhere located here, will be connected to the compressor, and then this is having a 2 concentric shaft which will be rotating. That means 2 RPM are being used, unlike in a turbojet engine where the RPM will be 1 or the shaft will be 1, because of fact that the blade what you call the fan will be rotating at a lower speed, that is the important. So, beside this, of course, this is the 2 separate nozzle which I have shown here, one is core nozzle, other is fan nozzle. So, now we will look at the turbo what you call shaft engines, and turbo shaft engine, if you look at, it is having the similar what you call core engines, except that it is connected to a propeller through a gearbox, and this gearbox is quite heavy as compared to the like your other engine components. Because why it will be heavy? If you look at your ICE engine or automobile engines, you do not have a very heavy gearbox. Why this aircraft engine will be have? RPM not only has to be reduced, but also the power level will be much higher. So, but however, this kind of engines we use find application in low speed flights and shorter takeoff, and also what you call like vertical takeoff kind of things it can do. And it is used in helicopters and small subsonic aircraft engines, and the schematic I have shown here. It is having a propeller, it is having a gearbox, compressor and combustion chamber. It is having a turbine, which will be one will be like high pressure will be connected to the compressor, where the low pressure will be connected to the propeller through the gearbox. And of course, you may get sometimes the thrust through the nozzle, but there is a turbo shaft engine, which will be only when power will be available in the turbo shaft, and no thrust being obtained in the exhaust nozzle as such. And it is having several application, as I told you, particularly for the vertical takeoff and short takeoff and landing, it is being used very much. So, let us look at the rocket engines. As I told, that rocket engines is basically the reaction engines which obeys the Newton's third law of motion. And in this case, no external material is really required to form the jet. What do you mean by this external material? Basically, you need not to take any air from the atmosphere. You are going beyond the atmosphere, then you need to carry both the fuel and oxidizer, such that it will be independent of atmosphere. And if you look at the performance of air breathing engine, will be dependent on the condition and of the atmosphere through which it will be passing through, whereas it is independent of. That is the beauty of these rocket engines, and it is, as I mentioned earlier, it is used for spacecraft propulsion and missiles. And there is a lot of development, however it is, but if you look at, we spend a large amount of our budget for the defense in the name of war, which is quite a bit. And it is not only in this country, but across the globe we spend lot of money and lot of resources, lot of manpowers for winning a war, and which is in future. So, therefore, it is very important to look at that we should not only be a part of this colossal wastage of resources, and see that how it can be utilized for the alleviation of poverty and other things, so that our country and other places can be live peacefully. So, I must tell you that although I teach this subject, but however, I feel that it must not be used and abused by this the warmongering people to have a war. So, however, there are several civilian application which can be done, and which must be used that thing. I must ask, because all of you, that as you people are the next generation or the leaders of this country, technical manpower particularly, and you should see that we should not really look at in this aspect, rather use that how we can use for the other man driven applications without spoiling the atmosphere. That is very important. So, if you look at this, produce the expulsion high speed hot gas through a nozzle. This is the basic principle which gives you thrust in case of air breathing engines, particularly class of your turbojet, turbofan and to turboprop, and also the rocket engines, whereas your IC engine based or the piston engine based is basically through the propeller. And here we use the propellants, which are basically chemicals, and as we are talking about the chemical powered engines, and the solid liquid or solid liquid engine, what we call it as a hybrid rocket engines. And we will be discussing little bit about electrical power engines now, and solar power engines and nuclear power engines. And I just want to give a bird's eye view of this thing, although this course is focused to on the chemical rocket engines and the gas turbine engines. But however, I just want to give a view, so that you can get a whole view, but we will be concentrating on the two aspect. One is rocket engine, other is the gas turbine engines. And in this course, we will be looking at the whatever the fundamentals are required to delve into the aerospace propulsion, particularly in the aspect of the gas turbine and rocket engines. So, let us look at solid propellant rocket engines, which is basically consist of a casing, and it is having a grain, and it is having a nozzle, and if you look at this is a constituents and it is having a igniter as well. So, if you look at it is the grain which burns in a predictable fashion and produces the exhaust gas, and we will be talking about how this grain design is required and other things towards the latter part of this course, and that is the crux of the solid propellant engine, solid propellant rocket engines. And this can be the problem with this solid propellant rocket engine is that once it is ignited, you cannot really put it off. However, in modern times there are several ways and means of putting it off, and where you can extinguish the combustion, throttle it and reignite it, all those things can be incorporated, rather have been incorporated in modern. So, modern design includes steerable nozzle for guidance, recovery like hardware and attitude control motors and thermal management of materials and other things. And let us look at a liquid propellant rocket engines in place of solid propellant, which is quite heavy, and then also it will function as long as the propellant is there, and it is having limitation. You cannot throttle, as I told you, that whereas the liquid propellant is having performance like a specific impulse, higher specific impulse, which we will be discussing little later on, defining it what it is. And if you look at the liquid rocket engine can have a monopropellant. Monopropellant means a single propellant, which will be containing both, act as both oxidizer and fuel, and bipropellant where like one is oxidizer, other is propellant, other is a fuel, and tripropellant which is rarely being used, but however, the three combination can be used. The example of bipropellant is the one is the liquid fuel, that is the liquid hydrogen which is being used, and liquid oxidizer like liquid oxygen is being used as a propellant. And I will just show you a schematic of the V2 liquid propellant rocket engine, which has created a havoc during the Second World War, which was being what you call developed by Germans, and it was the first ballistic missile which was used in the entire world in 1942 kind of things. And it has like for producing this 12,000 people died just to produce this, several because of under the Nazi, whereas it has created a lot of havoc in the England. So, this engine if you look at shown here, which is having a warhead, and this of course, the gyro is there, automatic gyro, guidance and control. It is based on the alcohol and water mixtures, right, and alcohol is nowadays not being used. Of course, the liquid oxygen was being used. It is a quite a compact engines, and it produces thrust, and it is having wing and jet vents to control these engines. If you look at your engine is this much, I mean this is a very small compact, it is having a large amount of fuel and oxidizer. So, also, and which is subsequently this V2 rocket engine is being captured and taken to USA, England and Russia. They have further developed this engine. Whatever engine we see, the father of those engines is basically V2 rocket liquid propellant rocket engine design. So, let us look at a hybrid engine where both the solid fuel like grain is being used and oxidizer, and it is having use because it is having several advantages over both the solid and the liquid propellant engines. So, either one solid or even the gas or the liquid can be combined together. It is not the only the liquid and solid, it can be combined, and hybrid rocket engine has advantages over both liquid and solid propellant rocket engine, especially in terms of simplicity, safety and cost. So, with this I will stop over, and if you are having any doubt, you can ask me a question.